Let's take a moment to review the meaning of the sine and cosine functions. If we have an angle whose initial ray is at the 3 o'clock position and has a measure of theta radians, and we center a circle of any size at the vertex of this angle, then the terminal point's horizontal distance to the right of the center of the circle, measured in radii, is cosine of theta. So cosine of theta represents the terminal point's horizontal distance to the right of the center of the circle, measured in radii. And then sine of theta represents the terminal point's distance above the center of the circle, again measured in radii. So the output of cosine and sine are both a number of radii. They take a number of radians, an angle measure, as an input, swept out from the 3 o'clock position. So if we have a meaning for the sine and cosine functions, we can begin to think about how theta and sine of theta vary together, and how theta and cosine of theta vary together. Okay, so in this applet, I have a lot of things going on. So first of all, I have an angle with a measure of theta, and I have the value of theta shown up here. Now, I have the terminal point shown here, and I also have the terminal point's distance to the right of the center of the circle, and this h, this variable h, represents that horizontal distance measured in radii. So h really represents the terminal point's distance to the right measured in radii. And I can vary the openness of this angle, and as I do that, theta and h will both update in value. And then on the right-hand side, I'm graphing theta on the horizontal axis and h on a vertical axis. So what we'll do is coordinate how theta and h vary together. When theta is equal to 0, the terminal point is at the 3 o'clock position, and it's 1 full radius length to the right of the center of the circle, so h is equal to 1. And then as we vary theta from 0 to pi over 2, so we vary that terminal point from the 3 o'clock to the 12 o'clock, that value of h decreases to 0 because the terminal point is getting closer and closer to being 0 units away from the center of the circle, like horizontally. So as theta varies from 0 to pi over 2, h will vary from 1 to 0. So in this diagram, we see that as that blue vector decreasing in length from 1 to 0. And then on the graph, we see that as theta varies from 0 to pi over 2, h is simultaneously decreasing from 1 to 0. So on that first quadrant there, we get a graph that looks something like this right here. Output decreases from 1 to 0. Now in the second quadrant, as theta varies from pi over 2 to pi, we have a horizontal distance of 0 radii, and then as we let theta increase, that horizontal distance becomes larger and larger, but it's negative, so it's decreasing out to -1. So when theta equals pi, h will have a value of -1 because the terminal point is 1 radii to the left of the center of that circle. And then on the graph, we see that as theta varies from pi over 2 to pi, h simultaneously decreases from 0 to -1. Then from theta equals pi to theta equals 3 times pi over 2, that horizontal distance will increase from -1 to a value of 0. So on the graph, we see that as from theta varies from pi to 3 pi over 2, h will simultaneously increase from -1 to 3 pi over 2. And then in the last quadrant, h varies from 0 back to 1. So in this graph over here, we have the graph of h relative to theta. We start at 1 for h, then h decreases down to 0, and then decreases to -1, and then increases back up to 0 and back up to 1. So this is what the graph of the cosine function looks like over the interval from 0 to 2 pi. And if you graph the cosine function on your graphing calculator, you'll probably see something that looks something like this, where we have a wavy looking function that goes infinitely far in either direction. So notice from 0 to 2 pi, which is about 6.28, we have the graph that we just plotted, but then the graph keeps going, and it looks like the graph just keeps repeating itself. This is because as theta is bigger than 2 pi, if we let theta vary from 2 pi to 4 pi, we just make another rotation around the circle, and that value of h just repeats the same cycle of values from theta equals 2 pi to theta equals 4 pi. And we can keep doing that over and over again. Now, let's examine how theta, the angle measure, and the point's vertical distance above the center of the circle in radii, v, vary together. As theta increases from 0, well, when theta equals 0, that terminal point has a distance of 0 radii above the center of the circle. So we see that here. There's no distance above. And then as that terminal point moves to the 12 o'clock position, the point's distance above the center of the circle increases up to 1. So as theta varies from 0 to pi over 2, v increases from 0 to 1, and we see that on our graph over here. On the next interval, we see that as theta increases from pi over 2 to pi, that value of v decreases from 1 back down to 0, because the terminal point moves from being 1 radii above the center to being 0 radii above the center. We see that in the graph over here. From pi over 2 to pi, we see what we expect to see. From pi to 3 pi over 2, the terminal point's vertical distance decreases from 0 radii to negative 1 radii above the center of the circle. And then from 3 pi over 2 to 2 pi, that vertical distance increases from negative 1 back up to 0. So once we've completed one full rotation, we have the graph of sine of theta relative to theta between 0 and 2 pi.